Good evening and welcome to Lowell Observatory and our ongoing celebration of the 24-inch Clark Refractor here at Lowell Observatory. It turned 125 years old this year, and it's got quite a legacy of historic research, of education, of inspiring people, both scientific and the public. And so it's been a great time celebrating it this year. With me tonight is one of our scientists, a planetary scientist, Dr. Jennifer Hanley. And a little bit later, Jennifer and I are going to talk about some of her research. We'll start out talking a little bit about some historic aspect of the telescope. We've been doing these programs every month, and each month we talk about something a little bit different. And so we'll talk about some of the cool characteristics of the telescope, and then I'll introduce a little bit of historic research that was done with the Clerk, because our featured object tonight is Neptune. And I'm not sure we're going to be able to get a view of Neptune because we have some clouds. And Sarah Bircher, who is the goddess of our public programs here, is trying, but we can't see through clouds. And so we'll just see how that goes. If not, we'll have some other images up. And then I also want to mention something really exciting and important. Just yesterday, we here at the observatory announced that on November 15th, we'll be reopening to general admission here at the observatory. So for 20 months, starting in March 13th, 2019, we either had to close initially because of COVID, and then we reopened, but in a very limited sense to reservation-only small groups. November 15th, we go back to general admission, and there's still some requirements. Everybody coming in has to show either a negative test, or if you don't have that, a proof of vaccination will work also. But eventually we'll get back to our final phase, which is unlimited, unrestricted opening. So we're really excited to be moving back to some sort of normalcy here and welcoming guests back to the observatory, and a program like this tonight that we'll still do some virtual programs, of course, but being able to do these things with guests at the telescope is going to be really fun to get back to. So the Clark telescope is just cool. It's such an icon. When you drive around here in Flagstaff during the daytime, you look up on the side of a hill and there's this big birthday cake sitting on top of the side of the hill, and it's been sitting there since 1897. And so it was here before Arizona was the state. So that the telescope, Lowell Observatory, Flagstaff, and Arizona have all kind of grown up together. And this telescope really represents Lowell Observatory because it's been here for most of the time. So let me just talk a little bit about some of the early history of it, some of the quirky things. And then we'll get to the really good stuff, the science, because that's what we do here, exploring and discovering. And Dr. Hanley is going to talk with us a little bit about some of the stuff that she's involved with exploring and discovering. So let me share my screen here. I'm going to bring up PowerPoint here, and in theory, a slide should be showing now of the telescope. This isn't the Clark telescope per se. This is when Percival Lowell established the observatory in 1894. He borrowed a telescope, two telescopes actually, put them in this dome. And they sat on the side of what we know today as Mars Hill. And this is the exact site of where the Clark would later be set. So we used this for a couple of years, or a year really. In 1895, Percival Lowell ordered a new telescope. And this is hard to read, and I don't expect anybody to really read it much, but I show this because Percival Lowell wanted a state-of-the-art telescope to be able to really study Mars initially. And so this is essentially the contract for that telescope. It's really just a handwritten agreement. You can see it's dated April 25th, 1895, and it describes the 24-inch refractor, and it's going to cost $20,000. So this is the agreement they have, and this is in our archives. So Percival Lowell orders this from Alvin Clark and Sons, of Massachusetts, the preeminent telescope maker of their kind. So he orders this telescope, but that old dome was too small. It wouldn't fit this larger telescope. And so Percival's assistant, Andrew Douglas, goes downtown Flagstaff, where he's made some friends. Godfrey and Stanley Sykes, they own a bicycle repair shop called Makers and Menders of Anything. And they said, we need a telescope dome. And the Sykes brothers asked, okay, tell us more about it. What's it gonna, how big is it and everything? And they said, well, telescope's gonna be 32 feet long. You're makers and menders of anything, so figure it out. And so they figured it out. The Sykes brothers owned a lot at Dale and Humphreys in downtown Flagstaff. So they built the top part of the dome right down there. And the Sykes brothers are very well known in town. Family is still here. The family still owns this lot. In fact, it's owned by, you might be familiar with Dinah Gabaldon, who wrote the Outlander series, which is now a TV series. Dinah Gabaldon is Stanley Sykes' great-granddaughter. One of the brothers who built the Clark telescope, his great-granddaughter is a world-renowned author and still owns the Sykes property in town. So they built the dome, then they tested out, they took it apart, they took it down to Mexico, where they also took the 24-inch refractor that was brand new, and they set it up down there because there is going to be a good appearance of Mars in the sky called an opposition when it gets pretty close, but it wasn't going to be so good in Flagstaff, you had to go more south. So they went to Mexico. This is the dome being set up, and you can see this is canvas that's covering the dome part. This is what it looked like when it was finished in Mexico. And they used it there for a year. Then they brought it back to Flagstaff. And remember where that telescope dome was? This is the original dome. If you look at the trees on the side, on the left, and on the right, and up in the upper corner, this is the original dome that was there. You can see that the Clark Refractor dome was put on the same site. So they set it up, still has the canvas. And if you looked at it from the inside, you can see this is still canvas on the sides. In 1898, they took the canvas off and they replaced it with wood and then metal. And that's the structure today. And so it's been pretty much like that since then. So kind of a unique history because the telescope and dome were taken out to Mexico for a while. Covered with canvas at one point, but still on the same location. So it really has a neat early history. And I think one of the interesting things about it are all the quirks. I mean, this is a telescope that was used for 125 years. And you can imagine through the years, you have handymen, you have times when we don't have much money. You have people that something breaks, you just rig it up, make it work. And so there's a lot of quirky things on the telescope that are kind of fun. This is a classic picture of Percival Lowell, and you see him sitting in his kitchen chair on this observing platform. The platform will go down, up or down, depending on the level of the eyepiece. This kitchen chair is still inside the dome. We still use it today. If you look from the other end, this is the eyepiece is way down here. This is where the lens is of the telescope. This is a continuous iris diaphragm. Sometimes when they're looking through the telescope, it's got a 2-foot diameter. And when they were looking at something really bright, you wanted to close it down so not as much light's coming in. And so down at the bottom here, there's a little dial, you turn it, and this diaphragm would close down all the way down to 6 inches. Or you could open it all the way up to 24 inches. So that's kind of a unique part of the telescope. Another thing that's pretty unique about it is the pit down in the bottom. And if you visited Lowell Observatory, you might very well have walked down into that pit. Some telescopes have elevator floors where the whole floor goes up or down. In this case, they put a pit so that the bottom of the telescope doesn't hit the floor, and they can put some equipment on the end, and you still have room to work. So that's kind of a neat thing. I don't know, one of the classic parts of this telescope is that it sits on 4 tires. And as far as we know, this is the only telescope dome in the world sitting on 4 tires. And that's to rotate the dome because you have an opening to look out. So you spin the dome around depending on what part of the sky you want to look at. Another kind of neat thing here, this is a little fuzzy actually, but these are the doors to the right. These are the doors that we open to look out. And so you have doors on the top and then these ones on the side. These ones on the side used to be operated with a rope and pulley, but in the 1960s, when cartographers were here mapping the moon, they wanted an easier system. So our handy person working at the observatory went to the airport and got 2 airplane landing gears and stuck them on there. And they're like big screws. And those are still there today. So the telescope still operates that way with those airplane landing gears. This is a great picture of the business end of the telescope. And this is pretty much what it looked like back in Percival Lowell's day. There is a bit of an anachronism with this box that you can't really see, but it's got a digital display. But mostly this is what it looked like. But right here, between these dials, looks like some sort of chain. That's a bicycle chain that goes back to the Sykes brothers. You remember they were bicycle repairmen. That chain is still on there today. So lots of really neat, quirky things about the telescope. And what we've been trying to do as we celebrate the Clark telescope every month is to talk about something different. And we haven't talked about some of those quirky things. So it's kind of fun to do that tonight. So that's just a little bit of a little historic tidbit about the telescope. And I guess we haven't mentioned this before on these programs, but if you want to learn more about the observatory, certainly come up and visit. Starting November 15th, again, we'll be open for general admission. You can also, in our gift shop, and you can visit the gift shop right now, actually. We have information about the telescope, like this book about it, which has a lot of great pictures. We also, in honor of this 125th anniversary, Miriam Robbins in our gift shop and her team have created a lot of fun commemorative things, T-shirts and mugs and such, celebrating the telescope. So that's something else that's we just wanted to mention that's available. So, it's always fun to talk about the history of the Clark and other parts of the observatory and some of the personality and quirkiness and everything. But of course, the ultimate thing is what's being done with it, and that's to carry out science, to explore the universe and try to answer questions that humankind has been asking for a long time, and to just learn more about the universe around us. With the Clark telescope, it is probably mostly known in terms of research for the work that Percival Lowell did in studying Mars in his pursuit of finding intelligent life there. But perhaps the most, in terms of just pure science, perhaps the most important discovery was V.M. Slipher's first detection of the expanding universe, starting in 1912. Well, while those were big focus areas, both V.M. Slipher and E.C. Slipher, his brother, did some imaging of Neptune, our featured object tonight. E.C. Slipher did actual imaging. V.M. Slipher, shown here with a spectrograph, took spectra of Neptune. And in fact, a spectra that he first captured in 1909, the scientists later used to discover methane in Neptune. So that was pretty important observations he made early on. He's remembered using the spectrograph for that expanding universe discovery and kind of establishing the rotation rate of most of the planets, including Neptune, as well as Venus and others. But this little tie with Neptune is kind of neat with it, as well as some of the pictures, some of the images they did. E.C. Slipher, VM's younger brother, did a lot of astrophotography with the telescope of not just the brighter planets, but Neptune and Uranus also. And he did some of the earliest techniques of what we think today as image stacking where you had photographic glass plates and combine images to make one good image. So there's some really nice history with the Clark telescope and Neptune and the outer solar system. The telescope was used off and on in the search for Planet X, which led to the discovery of Pluto. And the discovery was made with a different telescope. But also, after the discovery, scientists used the Clark telescope to study Pluto. So the telescope was used for a lot of outer solar system research, in addition to what we're kind of normally used to hearing. And that really laid the foundation. I'm going to stop sharing my screen here. That really laid the foundation, of course, for later research, because the history of what we've been doing here is really fantastic. But I think of it as the foundation for what we're doing today. And we've got one of the most powerful...
Sorry to interrupt. Before we get into the current science, there's been a couple questions in the chat about some of the intricacies of the Clark.
Okay, well, yeah, we'll get to those in just a second.
Okay.
And so the Clark, is such an icon of the observatory, and it allows our guests to, discover the universe just like Percival Lowell and our scientists continue to do. And it also laid the foundation for the important research that goes on today. And we're going to talk with Jennifer about that in just a minute. But as you said, we got some questions. So let's just take a look at these. Monique said, I'm not sure if that's Monique Schleifer. If it is, hello, Monique.
It is. She has a comment later. Hi, Grandpa. It
is. So Monique Schleifer is, hi, Monique. She's part of the Slipher family. Her father was David Slipher, and his father was VM Slipher. So really neat connection we have. And Monique, you have to come back down and visit, because we haven't visited since COVID started. Another question, is Neptune visible with binoculars?
We didn't answer her question yet, though.
She said, have the tires been replaced? I was so excited to talk to Monique that I didn't answer the question.
Yeah.
Actually, throughout the years, the tires occasionally go flat, and once in a while we even have a blowout. And inside that dome, it's like a cannon going off because the echoing. Through the years, usually our team has replaced a tire here and there as it needed, and they do it by using a car jack and jacking up part of the dome. And each tire is on its own axle, so they just take it off. It's pretty straightforward, and put the new one on. But just a couple months ago, our team worked with a local tire company and replaced all the tires, and so they're all new, and they're still a vintage size, and so they have to be specially made. But since they've been replaced, it's really squeaky in there because those new tires really squeal a lot. So Monique, great to have you in here, and we look forward to having you come back and sharing more of Grandpa's telescope with you. So Chris asked, is Neptune visible with binoculars? Do you want to talk about this, Jennifer, or?
You can go ahead.
Okay. Neptune wasn't discovered until 1781, and Uranus was 1846. You can't see Neptune with the unaided eye. With binoculars, you can just barely make it out, I think, but you can't really tell much about it. If you watch it night in and night out, you'll see it's changing position. But in terms of detail, because even through the Clark, and we would view it if we could, but clouds, even through that, it's just a kind of a bluish dot. It's not that big. In terms of where we are on Earth, it's just so far away that it doesn't look very big. So another question from Michael: how does the Clark compare to contemporary telescopes in terms of performance? Well, I can say that one important thing about telescopes is the size, especially the diameter of the lens or the mirror that's collecting the light, because telescopes are essentially light buckets. the more light you can collect. That's what astronomers are studying, is light. And they collect light and they study it with different instruments. So the bigger the light bucket, the more light you can gather, the better. The Clark telescope is one of the best telescopes of this kind ever built. And it has a diameter of 2 feet, 24 inches. The Lowell Observatory telescope, our largest telescope, the 5th largest in the continental US, is 14 feet in diameter. So it collects so much more light. We could use the Clark for research, but it's so important historically. And we have other telescopes with more modern equipment that are computerized, that are a lot more efficient, that gather, instead of looking through an eyepiece or attaching an old-fashioned camera with glass plates, it uses computer technology. So you can convert it and everything. The image you get for its telescope size is magnificent, but in terms of research, you would have to really renovate it a lot to make it really useful. So great questions so far, and great to have Monique on here. So Jennifer, this is the best part, because we love the history. I mean, I love the history and I write about it and stuff, but it's just to think that we've been doing this for 125 plus years, and you're now carrying the baton that Percival Lowell first started. And let's talk about some of your research, because while Percival Lowell himself focused more on Mars and the inner solar system, he did do some stuff in the outer solar system, and certainly research here at the observatory by you and some of your colleagues. We've certainly gone further out in the solar system and beyond. So let's talk a little bit about what you do. First of all, how did you end up being a scientist? What got you interested?
I've always been interested in space and planets. When I was little, just like many other young kids, I wanted to be an astronaut, and I never really grew out of it. And so I took a lot of science classes in school, and I eventually went to college for planetary science. My degree was in an interdisciplinary program called Science of Earth Systems at Cornell University. And the idea of that was to look at Earth as a planet. And so that really was the foundation for all of the research I've done so far. Then I went to the University of Arkansas for planetary science for my PhD. And, so I study the surfaces of a lot of different planets, in particular, thinking about the stability of liquids and ices across various planetary bodies, including Mars. So, water on Mars. I've done a little bit of research on that, following again in Percival's footsteps. But since I've come to Lowell, I've really gotten into using telescopes and also using some of the lab equipment that we have in partnership with Northern Arizona University to study those materials, the materials that make up the surfaces of these outer solar system planetary bodies, mostly the moons of the larger gas giants, but Triton, the largest moon of Neptune. We've done some really cool studies trying to understand what's going on there. Is it geologically active? Can we figure out if any of the material is mixed together?
And I want to talk to you about that interdisciplinary approach that you're taking, but I want to mention something that a recurring theme at Lowell Observatory, it seems like, is how history repeats itself, and how we just keep continuing. You mentioned that you went to school at Cornell, and we have a kind of a long connection with Cornell. They had a field station here up on the San Francisco Peaks nearly, about 80 years ago. And then one of our, I should say this in a way that doesn't make him sound ancient, but one of our senior astronomers, Larry Wasserman, went to Cornell, and his advisor was Carl Sagan. And then Ted Dunham was another scientist here who's now retired. And so long history of Cornell scientists. I'm not sure if we've had any others from Arkansas. So you're you're setting a trend there.
Yeah.
That's great.
At Cornell, my first advisor was Joseph Baverica, who was Carl Sagan's graduate student. So
okay. It's this lineage. You're only a couple degrees removed, I guess.
Yep.
So I think this is really interesting. We talk about, the Clark telescope, and it was used for doing visual observations. E.C. Slipher took images. V.M. Slipher did spectroscopy. So they were doing observations in different ways. But what you're doing is even more broad in terms of interdisciplinary. Is you're doing modeling, you're doing observing, you're doing computer testing and such. So let's talk about that a little bit and how they're kind of independent, but they all tie together.
Absolutely. And this is one of my favorite things about the work that I'm doing at Lowell, is that we have this research group that bridges all of these very perhaps discrete concentrations and areas of expertise. And so we have this laboratory down at Northern Arizona University where we can replicate the materials present on the outer solar system bodies. So for this Triton research, we actually mixed carbon monoxide and nitrogen together and measured the spectra of those two ices in different concentrations. So we do know that Triton has both carbon monoxide and nitrogen that have been detected spectroscopically through observations in the past. But we didn't know if they were actually mixed together or if they were just, we're, as Kevin mentioned, we're really far away. And so, it's hard to get very good spatial resolution on those small planetary bodies. So we measured the spectra of the mixtures so that we can start to understand, does the spectra change depending on if they are mixed or not? And one really surprising thing that we found was that not only do they shift a little bit from the vibrations and the interactions of the molecules, but in fact, you can create an entirely new spectral feature. And so if we start to think about the chemistry of what's happening, and I have more of a chemistry background for the planetary systems, so we started to work with some collaborators in the chemistry department at NAU, and we modeled a carbon monoxide molecule and a nitrogen molecule, and we actually put them next to each other and tried to figure out what is happening. How do we have an entirely new spectral feature happening? And it turns out that a single photon of light comes in and excites both molecules simultaneously, and we get an entirely new feature. And so we use that feature to go to a telescope. We use the Gemini telescope with a spectrometer called IGRINS, which was formerly at the Lowell Discovery Telescope.
And can you tell a little bit about Gemini, where that's located and how big it is and everything?
Yeah, Gemini. So we use the Gemini South telescope, which is around 8 meters. I'm not sure on the exact number, down in Chile. And it's, in fact, we were really fortunate because the timing worked out that they were looking for targets at that time of the night, in the fourth quarter of the night. And we didn't, because Triton's so bright compared to a lot of other things that people are using, especially with an 8-meter telescope, we didn't need too much time, or as much time as maybe some extragalactic astronomers might need. And so we were able to get some data really quickly, pretty fast turnaround, and we're using this really high resolution spectrometer. So, being able to see very narrow features, which this band is weak and narrow. And so it's really difficult to differentiate it if you don't have a really good instrument and telescope. We actually found that band on Triton. And so we showed that the carbon monoxide and the nitrogen must be physically mixed together, because that's the only way you can get that photon to excite those molecules. And so this is a really interdisciplinary project that it perfectly encapsulates the type of research that we're doing in our research group, where we're using laboratory experiments with chemistry and modeling, numerical modeling and simulations to understand what we're seeing in the lab, and then also observations using telescopes. And these all feed into each other, right? So there's other things where we look at a spectra from the telescope and go, what is that? Let's go look at that in the lab. Or we don't understand what's happening in the lab. Can we ask the modelers to predict what we should be seeing under these conditions? And it's all very synergistic and really fun and exciting.
And it is kind of a newer way of something that was done years ago. Again, this interdisciplinary approach. Back when Percival Lowell was searching for a ninth planet, he had his calculators, his computers, his people like Elizabeth Williams, who, based on the motions of Uranus especially, were trying to mathematically figure out where this thing should be, as well as doing observing. So it was using different techniques supporting each other. So kind of a tradition that goes back a long time at Lowell is this interdisciplinary approach. And I see we have a question for Monica, and Jennifer, maybe you've answered this already. What's your most surprising discovery in your research?
Yeah, well, I think finding a new band was pretty interesting. It's really not been talked about very much certainly in planetary science. Even the idea that you could get new bands by putting different molecules together. The laboratory work, especially the laboratory work at these outer solar system temperatures, we're really just getting into it now. It's really difficult and challenging to get the right conditions for the outer solar system. I mean, Pluto is 40 Kelvin, that's only 40 degrees above absolute zero. And the Kuiper Belt objects are even colder. So we have to get to really cold temperatures to, be able to even look at what's happening. And then when you start thinking about water ice, for instance, that's the bedrock on Titan or Pluto, right? That's the rock. That's what you have mountains made out of. And so what is really happening in these outer solar system bodies? It's analogous to Earth, where you have rocks and mountains and sometimes rivers and glaciers, but the materials are completely different. I think actually my most surprising discovery would be when we saw the formation of two different liquids in equilibrium with each other in simulations for the lakes and seas on Titan, and that's the large moon of Saturn. And so Titan's the only other body in our solar system that has liquids on its surface. And so I think that's a really, really interesting planet to study as well.
And Titan is really of interest because the possibility of some sort of life markers that are there. Maybe you can talk about that a little bit and some of the work that's being done related to that.
Yeah, so Titan, of course, has these liquid lakes and seas of methane and ethane, so hydrocarbons, organics, and it has this haze that is made up of photo-dissociated methane and mixed with nitrogen and hydrogen and carbons. And so it's very likely that the ingredients necessary for life are present on Titan. Titan also has, as I mentioned, a water ice bedrock, and it also has a subsurface ocean beneath that crust. And so its crust is made of water ice, but it has a subsurface liquid water ocean beneath that. And so it's very plausible to think that if an impact, a meteor hit it, it could punch through the crust and actually have some amount of liquid water interacting with the surface. There's a possibility that there's what we call cryovolcanism. And so you have, instead of magma coming from underneath, maybe you have liquid water coming up and creating a volcano of water. In fact, the Dragonfly mission, which NASA is going to be launching, in the next few years, and it's going to go to Titan, and it is a relocatable lander. And so it's actually going to drill into the surface and move around. And one of the key questions that it wants to answer is about habitability and astrobiology. How much does the organics interact with the potential water ice? Do we need water for life? That's another really important question that we don't have the answer to yet.
And here we are again repeating, our founder,
right?
Asking some of the same questions in a different way, with different technology and everything, but still looking at water, looking at life and such. It's just is neat how we go through these cycles a little bit. You were talking about cryovolcanism a little bit, and maybe you can touch on that a little bit, because scientists have certainly observed it on other planetary bodies. Maybe you can talk a little bit about that and just what that looks like, and how it compares to like volcanism that we think of here on Earth.
Right. Well, that's actually a difficult question to answer. And so we do think that there's evidence for cryovolcanism on some of the other planetary bodies, including Titan, perhaps Pluto, even Ceres potentially. Does Europa count if it has plumes? Does Enceladus count with its geysers? I think that this is a really interesting question. We always try and put things in terms of what's happening on Earth, right? And so we call it cryovolcanism. Does that mean it only water? Are we only talking about water? But already we're changing what volcanism even means. And so why do we have to limit it to water? Could we have nitrogen liquid flowing on Pluto, maybe, or something? And so I think this is a really interesting branch of planetary science where we're going to have to be careful what we call things, or just be conscious that when we call something volcanism or cryovolcanism, there might be analogs to what's happening on Earth, but it's not going to be the same, because water is actually really unique, and water affects everything we have here on Earth. One of the reasons we get volcanism on Earth is because the water basically is lubricating when you have plates sliding underneath each other. And so does that happen on other planets? I don't know. We don't know of any other planets that have plate tectonics. So then we have to start thinking about hotspots. So things like Hawaii is a hotspot volcano. So it's just moving over something that's warm in the mantle. And I don't know. We really don't know. It's a really fun, fascinating question, not just for the volcanism aspect of it, but all of the geology and the geochemistry thoughts of what is a glacier? Do glaciers move the same way if they're made out of nitrogen than if they're made out of water ice?
And that's a really interesting perspective, because that's so much of science and astronomy through the years, especially planetary sciences. If we're going to look for something, we look for what we're familiar with, because we can recognize it. But like you said, it doesn't mean it works the same way. Right. And so it really is fascinating. Like, the thing of looking for life. We look for, we think of life as a carbon-based sort of thing, but it doesn't have to be. It really raises a lot of interesting possibilities. And so it's fun that these kind of questions are still, stumping you and other scientists. That's what makes it fun, because, really, it always feels like the more we learn, the better the telescopes we have, the more questions we get.
Absolutely.
Because we dig deeper, but there are a lot more questions. So it's really exciting research. We have another question from Nikki. And Nikki, I think you're Cody's mom, if I'm reading this right. Cody Half Moon is our our marketing manager. The question is, was it the chemistry research that bred it rained diamonds on Neptune? What does that really mean?
Yeah, so not my research, but in general, people can model what's happening at depth in all of these different planets. And so I believe the idea of it raining diamonds is that the pressures are so high in the center of Neptune. So Neptune is a giant gas ball. But as you get towards the center, it's higher and higher pressure. So similar to how you would, as you swim in the ocean, you have the atmosphere above you, but then you have the water above you too. And so you have this extra pressure as you go towards the center of a planet. And so the pressure is so high that the carbon gets pushed together into diamonds. And so it's basically condensing into rain, and it's raining through it because it's not solid per se, right? It's not like the way we form diamonds on Earth, where it's in the middle of a, metamorphic rock, but rather that the carbon itself is just changing into diamond. And then because it's heavier than whatever it's surrounding, it'll actually fall down and rain.
Okay. Yeah, I mean, I think a lot of people would like to see diamonds raining from the sky.
Right.
Cool.
Yeah, I think that there's some exoplanets that they predict have diamond rain.
It's so neat. You have that image of the Clark telescope behind you, which was, one of a very powerful telescope. It's still a very great telescope for viewing. And now you're using today's state-of-the-art instruments to do research, as well as, like you said, laboratory analysis and modeling. Computer modeling changes how we do science.
Absolutely.
And so it's really, the interdisciplinary approach, and it's not just with astronomy, almost any science, you really get a more well-rounded answer to things usually because you can test it in different ways. So I think that's really great. We have just a couple minutes left, so if anybody has any more questions for Jennifer, particularly, this is a great opportunity to talk to a real scientist here at the observatory, and really, really exciting because Jennifer is one of our, you've been here, 3 years, 4 years? Something like that.
I've been here for 6 years now.
6 years, okay. Double that. It seems like you just got here.
It does feel like that. I think the pandemic has just time doesn't mean anything.
That doesn't count, right?
Yeah.
But just the research that you're involved with, and it seems like, we have weekly notices that come out from our director, Jeff Hull, about research going on. And throughout time, you were doing research on Mars, really important stuff, and Triton, and Neptune. It's really neat how many different things you're working on. And that's, some scientists study just like Dave Schleifer studies just comets, and there's a lot to study with comets. But with you, it's not necessarily specific body, but I guess maybe general types of bodies, but it's a lot of different things you're looking at.
Yeah, I think it's in the way I view it is a process, right? So I'm interested in how do we create liquids on the surface, which of course ties into habitability. If it happens to be liquid water on the surface, then that's a pretty easy case to make for life. If we're talking about liquid methane and ethane, I don't know. That's an interesting question, but I still think it's pretty fascinating to think about where things freeze or precipitate, or just start to think about ocean circulation patterns on Titan with methane and methane rain and methane rivers and nitrogen glaciers on Pluto and Triton. And so, it's kind of more of a process across the solar system.
Yeah. Well, we're going to go in just a second, but I think this is a good way to end because it kind of comes full circle. We had mentioned that, some of the early research with the Clark telescope of Neptune was VM Slipher with the spectrograph, and now his granddaughter is asking, how does the modern spectrometer or spectrograph compare with that, like the VM used, in terms of sensitivity, how easy it is to use, and such?
Yeah, so I'm not terribly familiar with the spectrometer that Slipher used back in the day. I can say that the spectrometers that we use now are incredibly powerful. So we have a spectrometer on LDT called Express, and the resolving power of that, it's to look for exoplanets. And so it can notice a 10 centimeter per second change in the wobble of a star to look for an Earth-sized exoplanet around it. And so the spectrometers are incredibly more precise. They also go to a CCD often or use a fiber. And so they're a lot easier to use because it goes to a computer and we can process that data quickly and do a lot of manipulation with it to, I should say processing, to take out atmospheric effects and things like that. So,
and so much of what VM Slipher was doing was figuring out how to use it. I mean, it wasn't really established yet. So he really made important contributions in just figuring out how best to do them. And we're out of time, but we have one more question, Jennifer. So real quick from Christopher, sure. Any evidence of hydrothermal vents on Titan or other planetary objects in the solar system?
So there is a lot of predictions that we'll have hydrothermal vents on a lot of these other planets. The best case that I've heard of is probably Enceladus and likely Europa, possibly Europa. But Enceladus, so we don't see it, but given, so Enceladus is one of the moons of Saturn, and it has these geysers that come out of the South Pole. And given the composition of the, water that's spewing out of the geyser, we're pretty sure that it's interacting with a mantle, a rocky silicate mantle, similar to Earth's mantle. And the fact that it's interacting and it's warm, probably because of tidal heating from Saturn, indicates that there is probably some amount of hydrothermal interaction occurring between the mantle and the subsurface ocean on Enceladus. Europa has similar conditions where it has a lot of tidal heating and tidal friction from Jupiter and the other Galilean satellites. It's long been predicted that Europa probably has some amount of hydrothermal vents at the bottom of its water ocean beneath the ice crust.
Okay. Well, like this happens all the time. We're out of time. It goes really fast. This is such great stuff to talk about. So Dr. Jennifer Hanley, thanks for joining us tonight.
Thanks for having me.
If anybody watching has further questions, you can always contact us at the Observatory and, keep these discussions going. We're really glad to talk about this stuff. So thanks everybody for joining us tonight. Thanks Cody Halfmoon, Maddie Mooney, Danielle Adams, our behind the scenes gurus for making everything work. Thanks Dr. Jennifer Hanley, and thanks everybody for watching. And we'll see you next time as we celebrate the night sky.
Good night.